Okay, we're going to start the circuits review. It's include a little bit of new stuff that we didn't discuss last year, but it's going to be divided up over a variety of different videos, but we're going to do the first few slides now so that we can go through this and then you can pick up the next video from there. So just to remind you that current, let's start about current. Current is the rate at which the electrons are going to flow through the circuit. The symbol for current was the letter I, capital I, and the unit was amps. We define it as the flow of positive charge from the higher potential or the positive side of the battery to the lower potential. Even though in reality it goes the opposite way, it's negative charge flowing from the negative to the positive, we're going to use conventional current as defined by Benjamin Franklin to be the flow of positive charge going from the positive side to the negative side. You can calculate the amount of current that exists in an object or in a circuit if you know how much charge is passing in a certain amount of time. You can just use this formula. Current is change in the amount of charge divided by the amount of time it takes for it to flow. So it's a rate of flow of charge. And if you want to control the current in a circuit, you can control it two different ways. You can either change the voltage, the total voltage of the circuit, or the power supply, or whatever you have, or change the resistance of the circuit. Those are the two things that will help control the current. If you want to know microscopically what's going on with the current, it's actually an overall flow of electrons, but the electrons aren't just shooting through the wires, they're actually kind of drifting around inside the wires, but overall they will move in one direction. So if you watch an electron move around inside of a wire, it'll kind of bounce all over the place a little bit, goes a little bit all over the place, but over time you'll see it kind of drift its direction, and so, kind of in a certain direction. So when we turn on a circuit, let me go back. When we turn on a circuit, or plug a circuit in, what we're really doing is we're just getting the electrons to kind of drift along inside that circuit, and they'll come out of the battery, they'll drift along, they'll come back to the other side of the battery. And it's kind of more like a conveyor belt. So you're turning on the conveyor belt and they're kind of moving along. And then if you disconnect the circuit, it's like shutting off the conveyor belt and everything just kind of stays in its location until you turn it on again. The reason the electrons drift along is because they feel a force from the electric field. The electric field comes from the battery itself. So the battery provides this electric field throughout the wire that provides the force that pushes the electrons along inside that wire. So that's really what's happening inside of a circuit. And this is something we didn't discuss in detail last year, so it might be a little bit new to you. We did discuss how to calculate the current in various types of circuits. For a series circuit where everything was hooked up one right after the other, every device has the same current going through it. So we said that the total current was the same for everything. And that's because when you hook up things one right after the other, like 3 resistors, and you never have a split, so here's your battery. If you never have a break in your circuit, a split up, there's no place for the current to be reduced anywhere or to split. So all the electrons have to go through every device, so the current is the same throughout that entire circuit. In a parallel circuit, when devices get split up into various branches, then you have the current that actually gets split up. The rate of flow in the various branches will vary depending on how much resistance each branch has. So the branches with more resistance will have a slower rate of flow through them. But altogether, all of those currents would add up to the total, whatever's coming out of the battery, a total rate of flow coming out of the battery. So that's how parallel circuits work, and up above is how series circuits work. To review voltage very quickly, voltage is what is supplied by the battery or the power supply. The symbol is V, the unit is V, of course. The circuit symbol for voltage is, remember, a long line and a short line, where the long line represents the positive side of the power supply and the short line represents the negative side. So a typical circuit diagram, you might have the positive and the negative side of a power supply. You might have some light bulbs. Remember, those are the drawing for light bulbs. You might have a resistor. Those should be all connected together. You could have a break where you have a couple of light bulbs or a couple of resistors in some sort of parallel branching. And then eventually you have to come back to the other side of the battery whatever you have in your circuit's got to return back to the other side. So that's just a typical circuit. So this would be a combination of series and parallel together. So if you remember, voltages in the circuit kind of were the opposite of current. In a series circuit where everything is in one, connected one right after the other, each of these voltages add together to give you the total voltage of the battery. So if this is my battery's voltage, VT, then each of these individual V's are going to add together to sum up to my total voltage. But in a parallel circuit, in this case, each of these devices gets the total voltage of the battery placed across it. If this is the only thing in the circuit, then each of these are equal to each other and would be equal in this case to the battery's voltage. If there's other things in the circuit, then all you'll be able to say is that the parallel voltages are equal to each other, but you may not be able to say they're equal to the battery. It just depends on what's going on, but they're definitely equal to each other. They all have the same voltage. Something we didn't discuss last year is this difference between what's called EMF or terminal voltage. EMF is something, it's got the best symbol I could come up with, it's like a curly E. That's really the EMF symbol. It's basically the total voltage of a battery, but it's not what's measured across the terminals, because every battery has a little bit of internal resistance just by the way the battery is made. It resists current a little bit. So we draw that internal resistance as a little bitty resistor right next to the battery. This yellow box represents what the total battery is, like what you're looking at when you look at a battery. It consists of inside a supply that provides a total voltage, and then also inside a little bit of internal resistance. So that overall, when you go to measure what's on a battery, you get what's called the terminal voltage. That's the voltage at the two terminals, the outsides of the battery. It's a combination of that total EMF minus a little bit of voltage that you lose to that internal resistance. So that's where you get this formula for this terminal voltage equals EMF, that's supposed to be that EMF symbol, minus IR. The IR is the voltage that's on that little bitty R value, that little bitty internal resistance. So it's not, the reason I'm adding this in is because you'll see this sometimes with circuits, but you're supposed to just treat this little bitty R as if it's part of the big circuit, and treat the EMF as if it's the battery's voltage. So when you have a circuit, you lose, the whole point is that because you can't make a battery perfectly non-resistive, every battery has a little bit of internal resistance that reduces the total effectiveness of that battery a little bit. And that's what this is representing, this whole idea that what you get on the terminal of a battery is a little bit less than what the battery actually has inside of it. Or this is VT, just because of the fact that every battery has a little bit of internal resistance. So if we work a problem with that, I can work a problem with you really quickly so that you can see how to do this particular problem. It says a 65 ohm resistor is connected to terminals of a battery whose EMF is 12 volts. So if I draw this out, here's my EMF, it's 12 volts. And there's a little internal resistance of half an ohm, so 1/2 ohm. And then this whole battery, so this little thing I'm putting the dotted line around is the battery. And this gets connected to a 65 ohm battery, resistor. So that's my circuit, and that's the part for the drawing. So the way you treat this is you just add the 65 and the half together. So your total resistance for this circuit would be 65.5 ohms, because this half just adds in with the 65, which makes my I total for this circuit equal to the 12 divided by the 65.5. Remember I'm using V total is I total times R total. Right? So that's the formula I'm using. It's Ohm's law, but for totals. So my I total is going to be my V total. In this case, that's going to be my EMF divided by 65.5. So I end up getting a total current of 0.183 amps. That's because there's this extra half ohm in my circuit, which comes from inside my battery. So now, if they ask you, so that's part B, the current. Now if they ask you the terminal voltage is the EMF minus the current times the little internal resistance. So this is 12 volts minus 0.183 times the half. So that ends up getting you a terminal voltage of 11.9. So whereas you might buy a 12-volt battery, you might only get 11.9 across the terminal. Actually, what ends up happening is when you buy a 12-volt battery, the EMF is actually greater than 12, so that you end up measuring 12 volts across the terminal when you first buy it. And then over time, that'll go down as you use up the battery. So they make sure that they give you an EMF greater than what the terminal voltage will be, so that you end up with your 12 volts when you go to measure it. But that's the whole thing with this. If you see one of these little internal resistances, you just treat it as one of the resistors in the circuit, and you go from there. All right, and then the last little thing that we need to review before we jump in is resistance, and that's the property that that material that tries to slow down the flow of the electrons. The symbol is R, the unit is ohm, if you remember that. The circuit symbol usually is just this little squiggly line, and any device that uses up the electron's energy is a type of resistor. And of course, all three of these are related using Ohm's law. Voltage, current, resistance, all related using Ohm's law. You can use Ohm's law for the total circuit, for overall voltage, overall current, overall resistance, or you can use it for any individual piece of the circuit. So any individual resistance with its individual current and its individual voltage. So if you remember from last year, when we were using totals, we did tot. V tot is I tot, R tot, when we were dealing with the total circuit. And when we were doing individuals, we did VI is I, RI, when we were dealing with individual pieces. All right, we're going to stop right there, and I'll pick up on the next video to help finish up, how to analyze the circuits.